Welcome to 39th lecture on numerical analysis. In this lecture, we will study Euler's method to solve first order ODEs, ordinary differential equations, and it is a numerical method. Before this, we have studied Runge-Kutta's method, which is a bit complex. So Euler's method can be thought of as a simpler version of Runge-Kutta's method. The thing that we will be given is a differential equation, a first order differential equation, dy by dx, we call it f of xy, and initial condition y of x naught is equal to y naught, and some step size h. These three are the same things that we are given in case of Runge-Kutta's method, right? And we proceed using a simpler calculation or using a simpler expression. Y of n plus h is y of n plus h times f of x of n, y of n. So this expression is simpler compared to the expression we studied for Runge-Kutta's method. So it can be thought of as a simpler version of that method, right? And we should also note that we start with the initial condition like we did in Runge-Kutta's method from initial condition, and we jump, and the size of each jump is h. And we keep on jumping unless we reach to the desired value of x, right? So the method seems simple. Let's move on and solve an example where f of xy is given to be dy by dx is y, and y of 0 is 1 and h is 0.1. So these are the three things given: the differential equation, the initial condition, and the step size. And now we are ready to proceed to find y of 0.2. So we will start from 0, jump size is 0.1, so we'll jump like this. We'll start from 0, the first jump will take us to 0.1, and the second jump will take us to 0.2. So we'll start with n is equal to 0, x of 0 is also 0, y of 0 is a 1, it's given in as an initial condition. So y of 0.1 is computed as y of 0, y of 0 is given to be 1, plus h times h is 0.1, f of x0, y is 0, y of 0, x of 0 is 0, whereas y of 0 is 1 given as initial condition. We plug all these values and y of 0.1 comes out to be 1.1. Now we are ready to take the second jump, and this is for n is equal to 0.1. so this will be doing for n is equal to 0.1, and y is 0.2, n plus h would be 0.2 because h is also 0.1, so n is 0.1, n plus h is 0.1 plus 0.1 is 0.2, so is equal to y of n, that is n is 0.1 plus h times f of n, y of n, where n is 0.1, x of 0.1, y of 0.1. We plug all these values and we reach to a value y of 0.2 is 1.21. so let's see the result that we get using the exact solution using the method we studied in last course, differential equations course we studied in last semester. So we proceed, and y of 0 is given to be 1, dy by dx is y, so if we take y here it becomes 1 over y, take dx here it becomes dx, and then we compute integral on both sides. So the log of y is x plus k, and then we take e to the minus e to the log of y and e to the x plus k on both sides, and it comes out to be c times e to the x, because e to the k is a constant and it can also be written as another constant c, like this. So y of x is c e to the x, and we put initial conditions, putting x equal to 0, y of 0 is 1, it's given, so c comes out to be 1. So the exact solution is y of x is e to the x, and we put 0.2 here, e to the 0.2, and e to the 0.2 is very close to 1.21. Let's see what e to the 0.2 is. Calculator, e to the 0.2, so e is 2.71828 to the 0.2. Where is x to the y 0.2, so it comes out to be 1.22. So it comes out to be 1.22, whereas the approximate answer is 1.21. So the exact answer is 1.22. And now we can calculate the percentage error as 1.22 minus the approximate answer 1.21 divided by the exact answer 1.22 times 100. So this we can compute using the calculator. 1.22 minus 1.21, so this is 1.22 minus 1.21 divided by 1.22 times 100. That was 0.008 times 100. It's almost 0.8%. So the answer is a very accurate method. It gives a percentage error equal to 0.8%. So it seems to be fairly accurate. Fairly accurate method. Which method? Euler's method. That is a fairly accurate method, but it's not as accurate as Runge-Kutta's method is. So it is less accurate compared to Runge-Kutta's method, but it is fairly accurate. Right, that's all for this lecture. Thank you.